So yeah, thank you everyone for joining in by Zoom today for the third seminar, I believe, of this season. And this is by our beloved Alex Maloney, who is faculty at McGill University in physics, the string theorist from McGill. And today he'll tell us about the connection between quantum gravity and the Siegel-Weil formula. So without further ado, Alex, the floor is yours.
Thanks, William. So it's great to be here. It's great to talk about this. Let me encourage anyone who feels okay doing so to turn on their cameras so that I am not lecturing into a void. So it's good to see everyone. I think we all understand the pain and anguish of lecturing into a void of blank little boxes. So it's great to see everyone. Also, let me encourage everyone to stop and interrupt me at any point if you have any questions. I'm very happy, as always, to be pulled on a detour of some sort. So if anything I say is mysterious, confusing, or particularly interesting, definitely stop me, and I'll talk about it at length. Also, I should preface this by saying that this is a somewhat unusual talk in the sense that, I'm a physicist talking about a mathematical subject to mathematicians, by and large, well, physicists as well, but a lot of mathematicians. And so what I'm going to try and do is use, to the extent that I can, a language that will hopefully make this accessible to mathematicians. I'll surely fail, but when I do so, let me know. And to the extent that I am able, I will try and rectify that situation. So I'm going to try and not use a ton of jargon and try and keep things as accessible as possible. And in particular, I'm going to be using some sort of highfalutin number theory ideas in this talk. So please stop and interrupt me and ask questions. And, I have my own I have my own way of thinking about these sort of number theory ideas that I think are really quite different from the way that a professional number theorist would think about these. And so please, I welcome any input or comments from the audience on that.
Okay, good. Here's a comment.
Yes, please.
You say we're all mathematicians.
No,
more than half of the audience have their degrees in physics.
Well, let's put it this way. A mathematician is not defined by what you have your PhD in. Let's put it this way. This is a talk at the CRM. A mathematician is defined as someone who is more mathematical than I am. Okay, that is my definition of a mathematician. And so by that definition, you are all mathematicians. Okay, good. And a physicist is defined as someone who is more physics oriented than I am. Okay, great. So I'm going to be talking about some work that I did last year with Edward Witten. I'll also, if I have time, comment a little bit more on some work that came out since then. But I should also mention that the paper that we put out last year was coordinated with a submission by another group involving Henry Cohn, Tom Hartman, Amir Tajdini, and Nima Afkamijeri. So, they were working on largely similar ideas. I think their perspective on it was actually quite different from ours. And so, if you're interested in this stuff, I encourage you to not just look at the paper that I wrote with Edward, but also that this other group wrote as well. In some sense, I think they have a point of view that's much more influenced both by Henry Cohn, who is a mathematician, not just by my definition, but by John's definition as well as taking more of a so-called conformal bootstrap approach to the subject. But I'd like to begin with as broad an overview as possible, just to explain my motivations for this talk. So quantum gravity is a mystery. And there are many ways of trying to think about quantum gravity and trying to understand what quantum gravity is. But for the purposes of this talk, the way that I want to think about quantum gravity is that it should be a sum over geometries. And what do I mean by that? Well, I mean, literally an integral over a space of geometries, or if we're thinking about gravity as general relativity, a theory of Riemannian or pseudo-Riemannian manifolds, then it should be an integral over a space of metrics. So, for example, one way of thinking about the problem of quantum gravity is that it is the problem of trying to compute an integral, okay? Here, I've given a schematic formula for this integral. It should be an integral over a space of metrics on some manifold, weighted by a factor that is the Einstein-Hilbert action. So in particular, if we're studying Einstein gravity, then quantum Einstein gravity should, in some sense, be described by an integral over a space of metrics weighted by this Einstein-Hilbert action, which is the square root of root g r, where r is the Ricci scalar, integrated over your
M is 4-dimensional?
I have not specified on this slide, but on the next slide, I'll specify which dimensions I'm interested in. At this point, it could be arbitrary. The only important thing to notice, or one of the only things to notice here, is that this action is dimensionful. And so I put a dimensionful constant there in order to weight the action, which is h bar. Okay. So the problem, of course, is that this integral doesn't make sense. And we don't really have an idea of how to compute such an integral, or even under what circumstances such an integral could be really rigorously well-defined. But over the last couple of years, there has been a lot of work that indicates that the resolution to this puzzle could come from a surprising place, namely from the physics of disordered systems. And here I'm using disorder in the way that a condensed matter theorist might use the word disorder. In particular, it's related to what a condensed matter physicist might call quenched disorder, where you start by thinking about a quantum mechanical system with a bunch of coupling constants. And instead of considering one single instance of this quantum mechanical system with particular values of the coupling constants, you consider many instances of this quantum system where the coupling constants are drawn from some sort of statistical distribution. So for those of you who have studied spin glasses or something like that, this is a very familiar set of techniques. And the thing that really is remarkable is that there's a surprising amount of evidence that has now accumulated that the sort of approach that applies to the physics of disordered systems can also be used to think about quantum gravity. And in particular, the basic slogan is that there is a sense in which quantum gravity appears to be given not by a single quantum mechanical system, but by an average of many quantum systems. And
sorry, again, is it Lorentzian or Euclidean?
So right now I'm talking about Euclidean signature. So for example, in this formula, I'm thinking about a Euclidean metric, which is why I wrote the square root of the determinant of the metric instead of the square root of minus the determinant of the metric. There are many words that I could say about Lorentzian signature. For the purposes of this talk, I would like to focus on Euclidean gravity. So here, what I mean by that is that this integral over a space of metrics should be regarded as an integral over a space of Riemannian metrics on some manifold. But there will be much that one could say about Lorentzian metrics as well, and Lorentzian quantum gravity. And indeed, there are many closely related things we could say. And actually, if I have time at the end, I'll show a slide related to Lorentzian physics, if you like. So the thing that is really remarkable to me is that this idea that gravity should be regarded as an average over many quantum systems can in some places be made excruciatingly precise. So actually the first instance of this is not due to me, but due to a group at Stanford, authored by an author named Stanford, actually, along with his collaborators. This is a very lovely paper by Saad, Schenker, and Stanford, who showed that a certain theory of gravity, a very simple theory of gravity, where you're working in 2 dimensions, so an integral over a 2-dimensional space of metrics, is in fact completely equivalent to a random matrix theory. Okay. That's something that we could talk about in more detail if you like. But that was, I think, really the first indication that a theory of gravity could, in some sense, be rigorously defined as an average of many quantum systems. And what I'm going to be talking about today is an attempt to discuss a sort of more, a richer theory of gravity than the simple theory of gravity that is equivalent to a random matrix theory, where one can nevertheless do the exact same thing. And in order to do so, I'm going to use some tools stolen from number theory. And in particular, I'll use the Siegel-Weil formula that was in the title of my talk today. In order to do so, what I'm going to have to do is specialize a little bit. And so rather than talking about a general theory of gravity, I want to talk about a theory of gravity in 3 dimensions. So now I'm going to specialize, and instead of thinking about Einstein gravity in some general number of dimensions, I'll talk about Einstein gravity in 3 spatial dimensions, 3 space-time dimensions. But because I'm working in Euclidean signature, that's just the same as saying 3 spatial dimensions. And so then I can be a little bit more precise about what I mean by this integral over a space of metrics. What I mean now is an integral over a space of 3-dimensional geometries, a space of 3-dimensional metrics. So these are metrics G on some 3-manifold. And this sum over geometries is going to be weighted by the usual Einstein action, basically the same thing that I wrote down on the previous slide, with the small modification that it has a negative cosmological constant. So I'm going to weight it by not just the integral of the Einstein-Hilbert action, but also by the volume of this 3-manifold. And the final interesting ingredient is that when I compute this integral, I'm going to compute it as a function of data living at the boundary of space-time. So in particular, what I want to do is I want to think about this integral over a space of 3 manifolds, but it's an integral over a space of 3 manifolds with some fixed boundary that I'm going to call sigma. Okay, so you want to think about sigma as some surface, some 2-dimensional surface, and I want to sum over all geometries whose boundary is that surface. So if you like, you could think about it as a sum over ways of filling in that surface.
2 questions.
Please.
This is just my ignorance, but 3-dimensional standard quantum gravity, I believe, is renormalizable, isn't it?
Well, it's interesting. 3-dimensional general relativity is at the level of perturbation theory a topological theory that can be written in terms of a Chern-Simons theory. And that's actually going to reappear later on in this talk. So it's not just renormalizable, but at the level of perturbation theory, it's a topological theory. That's sort of why we're going to be able to say anything that is precise.
Okay. My second question, is this a sort of ADCFT type of thing? Is the boundary?
Well, let me get to that.
Is that a conformal field thing?
Yeah, let me get to that in a second. So we're thinking about the sum over 3-dimensional geometries. We use sum over manifolds with a fixed boundary. Now, it turns out that when you define this theory precisely, when I say fixed boundary, I need to say exactly what kind of boundary conditions I'm putting on my metrics. And so I'm really integrating over a space of metrics with some specified set of boundary conditions. And although I won't go through any of the details, it turns out that when you're studying this theory of gravity, so you're studying an integral over Euclidean geometries with some fixed boundary. And it turns out that what you need to do is you fix only the conformal structure of the boundary. And this path integral, this integral over a space of geometry, should be regarded as a function of the conformal structure of this surface. And we can now think of it as a Riemann surface that lives at the boundary. And
one more stupid primitive question. When you vary the metric, Are you fixing the topology of the manifold, or are you varying that
That's
too?
the important question. Okay, so there's a huge amount of argument in the community as to how exactly the sum over geometries should be defined. And there has been increasing evidence accumulated over the last 20 years, I would say, that you need to include a sum not just over metrics on manifolds of a fixed topology, but also a sum over topologies. And indeed, what we're going to see in some sense is this sum over topologies is going to appear precisely from this disorder averaging procedure that I'll outline for you. For a variety of reasons, it has been suspected for a long time that the sum over geometries should include a sum over topologies of the three manifolds. So here you could think about this as a sum over topological three manifolds that fill in our boundary. That's something that is going to appear here, yes. But people have argued for a very long time about, exactly what topologies should contribute, how you should think about them, and so forth.
But is the topology of the boundary fixed?
The topology of the boundary is fixed. So the name of the game is to compute this sum fixing the topology and conformal structure of the boundary. Okay. So for example, if your boundary is a torus, then you're going to be computing a function of the conformal structure of a torus, which for those of you who've studied these sorts of things is an SL2Z invariant function of the modular parameter tau that defines a torus, which you could also think of as a function that lives on the fundamental domain of the torus, if this kind of picture is familiar to you. Good. Okay, so the next insight, it comes from ADCFT. So the ADCFT correspondence starts with the observation that this path integral is a function only of the conformal structure of the boundary. And one way of getting a function of the conformal structure of a Riemann surface is to consider the partition function of a conformal field theory on that Riemann surface. Okay. For those of you who aren't super familiar with conformal field theories, don't worry. I'll give you a very rigorous, precisely defined example of the sorts of CFTs that I'm going to be considering. But the basic point is that a conformal field, so quantum gravity is something that we don't understand at all. Conformal field theory is something that we do understand. And it's something that can be defined, in some cases, completely rigorously mathematically. For example, some people define conformal field theories in terms of vertex operator algebras or modular functors and all sorts of fancy things like that. From my perspective today, the class of conformal field theories that I'll be interested in are free field theories. They're much simpler. They're characterized by even self-dual lattices, as I'll review in a little bit. But in any case, the basic point is that these conformal field theories are completely rigorous, well-defined objects. Okay. So the idea of the ADS-CFT correspondence is that this mysterious gravity path integral that we don't really understand very well is in fact equal to something that we understand perfectly well. Namely, it's given by some conformal field theory calculation. Okay. Now, this gravity path integral, although we don't understand how to calculate it exactly, we certainly know how to approximate it. And to some extent, we spend all of our lives as physicists coming up with techniques for approximating path integrals. For example, one way that you would approximate this gravitational path integral is with a saddle point expansion. Okay. So in particular, if you were working in a semi-classical limit, where h bar is very small, then you would approximate this path integral as the sum over classical geometries that I've labeled G0 here, okay? And you would have the action evaluated on this G0. Okay? So that would be the leading saddle point approximation to this integral, or stationary phase approximation to this integral. And then if you're very powerful, you could compute the first correction to that saddle point, and then maybe a second correction, and so on and so forth. And now, physicists have names for these different corrections to the saddle point approximation to this integral. We call them Feynman diagram. Feynman diagrams, right? So, for example, this term that I've called S1 here is what we would call the one-loop Feynman diagram correction to the classical action. Then, if you're very powerful, you could compute two-loop correction, and so on and so forth. Okay. So, a lot of our understanding.
I don't want to be finicky here, but you are talking about Euclidean field
Yes.
theory. Mm-hmm. So, is it really a saddle point, or is it a steepest descent?
So in order to define this precisely in a gravitational context, it's a little bit more complicated. I don't know if it's a little bit more complicated than this. For example, in the gravitational context, it actually turns out that there's a slightly subtle analytic continuation we need to do in order to actually regard this as an honest saddle point or calculation. The most, I think, satisfying way to treat this problem would be to define precisely a contour of integration through the space of metrics, go through a stationary phase argument, determine the G0 that appear in the sum by finding the correct stationary phase contour through a space of metrics. But to my knowledge, nobody knows how to do this, right? I mean, there are some cases involving Chern-Simons theories and topological quantum field theories where that procedure can be carried out precisely, but nobody knows how to do this in the case of quantum gravity. There's some hope that in simple theories of gravity, such as those in 2 and 3 dimensions, it might be doable, but that's not the direction that I'll be going today. No. Good. So to some extent, this ADS-CFT correspondence presents a kind of solution to the problem of quantum gravity, in the sense that if you could determine the conformal field theory C that gives a particular theory of gravity that you're interested in, then this gives you a rigorous quantum mechanically well-defined definition of what you mean by quantum gravity. And indeed, in certain extraordinarily fancy theories of quantum gravity, string theories, we actually know what conformal field theory sits on the right-hand side of this equation. But the problem is that the gravitational theories that sit on the left-hand side are extraordinarily complicated theories that look not much like the kind of gravity that we see around us. And in particular, they include Einstein gravity, but they also include tons of other stuff, tons of other degrees of freedom. So the sorts of theories of gravity where this ADS-CFT correspondence is understood precisely are theories of gravity that include not just a sum over metrics, but a sum over all kinds of other degrees of freedom. Not just, the other fields, like gluons and scalars and stuff like that, but new sort of stringy degrees of freedom that we don't even really understand terribly precisely at the quantum mechanical level. So what we would really like to do is understand this ADS-CFT correspondence for a simple theory of gravity that we could analyze rigorously, like Einstein gravity. Okay. So the question that I'm going to try and ask then is, what conformal field theory C could be dual to Einstein gravity? And it turns out that, as far as we can tell, the answer is that there is not a conformal field theory that is dual to Einstein gravity in 3 dimensions. But instead, the picture that is emerging is that the thing that is dual to a simple theory of gravity, like Einstein gravity in 3 dimensions, is not one conformal field theory, but many conformal field theories. And in particular, it is an average over many CFTs. So in particular, the picture that I believe is true, and that I'll be able to argue for in the talk today in a very, very, very limited, simpler context, is that the path integral of quantum gravity in 3 dimensions is not given by a single CFT, but by an average over many CFTs. So here I'm thinking about these CFTs are standard quantum mechanical systems, but there is a space of them. There is a probability distribution on this space, and the gravity path integral is given by the weighted average of the CFT partition over this space. Okay. And there are several sort of preliminary indications that something like this should be the case, or could be the case. The first is that there is an even simpler theory of gravity in ADS2, that is a theory of random matrices. This actually is very closely related, this observation is very closely related to topological recursion, which is a relationship between a certain class of matrix integrals and a certain class of geometric structures that arise when you do integrals over metrics in 2 dimensions. There's another piece of evidence related to what are called Euclidean wormholes. For our point of view today, I don't want to spend too much time talking about that, but for our point of view, the basic observation is that when people try and compute this gravitational path integral in situations where your boundary is disconnected, so it's the disconnected union of 2 surfaces, the result does not factorize. And a simple interpretation of that factorization is just that you have a non-trivial probability distribution. That is to say that this thing that I have called P of C here is non-trivial, because whenever you have a probability distribution, correlation functions won't factorize, unless your probability distribution is just a delta function or something silly like that. So the existence of these wormhole solutions of general relativity can be interpreted as evidence that there are, that in fact, gravity is some kind of ensemble average. I'm happy to talk more about this. This I think was initially emphasized in some papers that, well, the study of wormholes in quantum gravity is something that goes back many, many years. The idea that the existence of Euclidean wormholes would lead to a probability distribution on a space of theories actually goes back, I think, to Sidney Coleman in the 80s. And to some extent, what we're doing here is, trying to put that on a slightly firmer footing. And the final observation that I think motivated this idea that conformal field theories, that really gravity should be an average over many quantum systems, was motivated also by the fact that when you study theories like Einstein gravity and you try and make sense of them from a precise quantum mechanical level, it turns out that they have continuous spectra rather than discrete spectra. Okay. And what you're supposed to think of in your head is something like a theory of random matrices. So for example, if you take an n by n Hermitian matrix, then the spectrum of eigenvalues is a discrete spectrum. Okay, that's true. There's n of them. The n energy levels, if you think of your Hermitian matrix as a Hamiltonian. But if you consider an ensemble average over an infinite number of Hermitian matrices, then that discrete spectrum becomes a continuum. So for example, if you have a Gaussian probability distribution for the entries of a Hermitian n by n matrix, then the probability distribution for the eigenvalues becomes the famous Wigner semicircle. Okay. And so we should think about, so in retrospect, the observation that these theories of gravity have continuous spectra, whereas you would expect them to have discrete spectra, is maybe also another hint that there's some kind of averaging process going on.
Sorry, Alex, but
Yes,
the Wigner semicircle is the n equals infinity limit.
Sorry, I should have said that. Yes, so in large N, it's the semicircle, but yeah.
So
Was
you
there
along
any
the
other?
finite matrices. Yeah.
Well, I mean, there's still a probability distribution over eigenvalues for finite N. Okay,
Okay, but the semicircle is the n equals infinite limit.
that's right. Yeah. Okay. So my goal is to develop a theory of random conformal field theories that is analogous to the theory of random matrices. Okay. So how would we do this? Well, what do we need to do? The first thing you need to do is decide on a space of conformal field theories. Okay, I'll specify that in just a minute. But we need to decide on a space of theories. We need to decide a probability distribution on this space. And then you need to compute some averages and compare it to what you think your gravitational theory should be like. Okay. Now, this is a very hard problem. So for example, step one in this procedure has a name. It's called the conformal bootstrap problem. Solving it would be tantamount to solving quantum field theory, strongly coupled quantum field theory. Okay, which is, you would be rich and famous if you did that, but I'm not going to be nearly so ambitious today. So in particular, what I'm going to do is what we always do in physics when we have a problem that we can't solve. I'm going to add symmetries until I can solve the problem. Okay. And in particular, I'm going to add enough symmetries that I can carry out this procedure completely systematically. And I can go through, determine a space of CFDs, fix a distribution on the space, compute averages, and the result will look like a theory of gravity in EBS. And in particular, because I'm thinking about a three-dimensional theory of gravity, I'm going to talk about two-dimensional conformal field theories. And for those of you who've studied such theories, you'll know that such theories are characterized by a number that is known as the central charge. And in this dictionary that I've written down, this central charge is going to be 1 over h bar. Okay, so I'm going to use c and 1 over h bar interchangeably. And in the gravitational language, this central charge is basically given by 1 over Newton's constant. Okay. So it's the dimensionless parameter that is the coupling constant of my theory of gravity. It sets the size of quantum effects in this theory. Okay. So this slide is not so much the something that you would talk about in the introduction of the talk, but rather in conclusions. So this is the one slide summary of what I'm going to do today. So I'm going to consider a particular set of conformal field theories that have lots of symmetry. Okay. It turns out that this space of conformal field theories is very closely related to mathematical problems involving sphere packing on lattices. And that parameter that I called the central charge on the last slide, 1 over h bar, is the dimension of the sphere packing problem. So the mathematics of conformal field theories with this set of symmetries is related to the mathematics of sphere packing in d dimensions. Okay. So in particular, this was 1 over h bar. And so in particular, the semi-classical limit, the h bar going to 0 limit, is going to be related to the mathematics of sphere packing or of lattices in a large number of dimensions. Okay, so it turns out that on such a space of theories, there is a finite dimensional space of conformal field theories. Physicists know this as Narain's moduli space of CFTs. I'll write it down for you on the next slide. But there is a finite dimensional space of such theories. It turns out that we can compute the average of any observable in the CFT over this space of theories. And in fact, it turns out mathematicians did it some time ago. It's known as the Siegel-Weil formula. And the result is exactly what you expect from a theory of gravity. In particular, this Siegel-Weil formula is a sum over geometries, which we can enumerate, dressed by a classical action plus some loop corrections in the language of Feynman diagrams. The thing that is special about this theory of gravity is that in a general theory, there would be lots of dots there corresponding to higher loop corrections in the language of Feynman diagrams, but those all vanish in this theory. In the physics terminology, this is a theory that is one loop exact. Okay? So in the physics language, these geometries that would appear in this sum you would refer to as instantons. And so this is a case of a theory of gravity, where we can enumerate all of the instantons, that is to say, all of the saddle points. We can find all of the loop corrections in the theory, and you can sum them all up. Okay? It's a very simple theory, because in a normal quantum field theory, this is an incredibly difficult problem that is generally going to be impossible. But this is a very simple theory where we can just do all of that. Find all the instantons, sum them up. Find all the loop corrections, put them in the sum them up. And the answer exactly agrees with an average over a space of conformal field theories. Okay. So
can you spell out a little more how the U1 to the D cross U1 to the D acts?
That's exactly what I'm going to do. Okay. So this was intended to be a long-winded introduction where I tell you what I'm going to do, and then I'm going to go into as much detail as time allows me to. Good. So here's my plan. I'm going to talk about this space of conformal field theories and how I average over it using the Siegel-Weil formula. I'll talk about the gravitational interpretation of the results, and then I'll end with some confusion. I won't end with conclusions, I'll end with confusions. Okay, but let me pause and see if there are any questions. I have no agenda here. I'm happy to just talk about general stuff, or I can go and dive into more detail.
Well, maybe this is premature, but if you could actually write down the Siegel-Weil formula, it would be a big help.
That's where I'm going.
It's an integral of the space of moduli of higher genus.
Yep. No, it's a different. So that's exactly what I'm going to do. Okay. So let's talk how to average over spaces of CFTs. Okay. So what are the theories that I'm talking about? So in the language of quantum field theory, they're free field theories. Okay. So what do I mean by that precisely? I mean theories of maps from a Riemann surface onto a circle. So these are what we, in the physics language, would call theories of compact free bosons. Okay? And in particular, these are theories of D compact bosons, where D is some integer, that will be taken to be large if you want to make contact with a semi-classical theory of gravity. Okay. So how do I define such a theory? So the basic degrees of freedom of the theory are D scalar fields that I've called X here. Okay. P is an index that labels which scalar field that runs from 1 up to T. And these fields live on some surface sigma that I have written here. I'm thinking of it as a Riemann surface. So I've written it here using some complex coordinates, Z and Z bar. And in particular, I want to think about this as a free field theory, which means that the action of the theory is going to be quadratic in my fields. Okay? So what is the most general quadratic action that you could write down? Well, it's going to involve some sort of kinetic term. And if you think about it for a little bit, the most general kinetic term that you can write down is the one that I've written here. Okay? And the data that you need to specify in order to define such a theory is a symmetric D by D matrix that I have called G, and an anti-symmetric D by D matrix that I have called B. Okay. I've called them G and D because if we were giving a string theory talk, they would be the world sheet metric and world sheet B field of some string theory. So if you've studied string theory, you will be familiar with these things, but if you haven't studied string theory, you might be familiar with these things too. So this is the kind of theory that I'm going to be interested in. John asked about this U1 times U1 symmetry. So what is the U1 symmetry doing here? The U1 symmetry is the translations around that circle, S1, right? So the rotations of the circle give me a U1. If I have D circles, I get D different rotations. So there's your U1 to the D. And it turns out that I get a U1 to the D times U1 to the D, because you can treat a holomorphic and anti-holomorphic bits of the fields X separately. So you actually get U1 to the D times U1 to the D. So what does the space of such CFTs look like? Well, each CFT is labeled by these coupling constants G and B. And so the space of CFTs is parameterized by a set of coordinates that are this antisymmetric and symmetric D by D matrix. And so that tells you that the space of such conformal field theories has dimension D squared.
Is there any requirement of non-degeneracy of those tensors?
Yes. Yes. So G has to be a positive symmetric matrix. Okay. So no zero eigenvalues. Good question.
And is, I don't know if it's even dimension, but is B of maximal rank?
Nope, could be zero. Yeah. So although I've explicitly written down the action of the theory in terms of these coupling constants G and B, it turns out that there's a much more highfalutin way of thinking about the space of CFTs. And in particular, it is the space of even self-dual lattices of Lorentzian signature, of signature D comma D. Okay. How should we think about that? Well, this CFT is a space of maps from a Riemann surface into a torus, a D-dimensional torus, S1 to the D. And I could think about the space of toruses we map into as being the moduli space, the space of such conformal field theories. And that's what this moduli space is that is appearing. So in particular, the space of Euclidean lattices in D dimensions is given by O of D, right? Because you can get between any two such lattices by some O of D rotation. Here, we're getting Lorentzian lattices because, very roughly speaking, the holomorphic and anti-holomorphic parts of this field X can be treated independently. So in fact, the space of such theories is the space of even self-dual lattices. And you can think of those coupling constants G and B as coordinates on the space of lattices. And I've written down the space of lattices here. It's this double coset, ODD, modded out by, this is the important thing, ODD of Z. Okay. In the physics language, that ODD of Z arises because of what is known as T-duality. Okay. But in the mathematics language, it's just the space that any two even self-dual lattices that are related by some integral relabeling of their components give you the same lattice.
Is there some way to relate this to the Siegel upper half plane?
No, the Siegel upper half plane is going to appear later. Okay, this is not the Siegel upper half plane. This is what we would call Narain moduli. In the physics language, we would call it Narain moduli space. Good. And this is our space of CFTs. And so when I say average over space of CFTs, I mean integrate over this coset, ODD. Okay, good. Now, what is it I'm going to compute? So I've told you what my space of theories is. I now have to tell you what I'm going to compute. I'm going to compute the partition function of this CFT. Okay. So what is the partition function? Well, it's going to be an integral over these fields. That is to say, an integral over a space of maps from my Riemann surface into a torus, weighted by the action that I defined for you on the previous slide. Okay. Now, this is going to be a function of the Riemann surface that you choose. Okay. And so in particular, it is going to depend on the lattice lambda that defines your conformal field theory, as well as a function of the period matrix of your Riemann surface. Okay. That is to say, a function of the conformal structure of your Riemann surface. So, and to answer John's question, The period matrix omega is the thing that lives in Siegel upper half space. Okay. So the partition function that we're studying is going to be a function first of a lattice that defines your theory, and then of the Riemann surface, and it will depend on the Riemann surface via its period matrix, that is to say via its conformal structure.
So that's is that GPQ?
Yes.
So it's complex, but it's imaginary.
Oh, sorry, wait, sorry. If I understand, what do you mean by GPQ?
The GPQ appearing in your exponents.
GPQ.
You wrote down a theta function.
Yeah. So yeah, let me get to that. This GPQ is the metric that I defined on the previous slide, and this is
that's complex or real?
It's real.
Ah, okay. So that's not really okay.
Yeah.
I'll let you talk.
So the space of period matrices. Okay. So there's a couple little important details. The space of the space of conformal structures of a Riemann surface sigma is the moduli space of that Riemann surface. It turns out that for these free boson theories that we're considering, you can actually think of this period matrix just as an element of Siegel upper half space. That is to say, the space of complex G by G matrices with positive imaginary part. And in particular, although I won't go through the details, the point is that if you wanted to, if for a particular free boson theory, you could just go ahead and compute this partition function. I mean, it's a free theory. It's just not that hard. Okay. How do you compute the partition function? The action is quadratic, so you're doing Gaussian integrals. Okay. So in particular, you get what we would call a one loop determinant that I've written here, along with a sum over classical solutions. Okay. So that sum over classical solutions in the number theory language has a name. It's called a theta function. In particular,
so the fact that this is a sum over exponentials of quadratics, is that related to your saddle point approximation?
So this is a boundary CFT statement. So the thing that is going to happen is when we average, it's going to turn into a bulk sum over geometries. I think for those of you who aren't so familiar with this, a good thing to do is to consider the case where the surface sigma is a torus. So this is a function of the conformal structure parameter tau of a torus that lives on the upper half plane. In this case, the one loop determinant is a Dedekind data function. We could talk about where it comes from if you like. But the interesting thing from our point of view is the theta function, which is what a mathematician would be familiar with as a lattice theta function. Okay. And if you were at higher genus, you just get some fancier thing that we call the Siegel-Narain theta function because it was independently written down both by the mathematician Siegel and the physicist Narain. Okay. So this is all a little bit convoluted, but the point is that there is a fantastic mathematical gadget known as the SiegelWeil Formula, which lets us compute the average over the space of CFTs. So in particular, if I were to compute this partition function, and then I were to average it over the space of lattices, so I remind you that this average is just literally the integral over the moduli space of CFTs. So it's some integral over lattices. Turns out that you can compute this. And it's given by what we know, what is referred to as a real analytic Eisenstein series. Okay. So I don't want to go through unpacking too many of the details, but I'll just tell you the general structure of the result, which is that this Eisenstein series is a sum over the modular group of your surface sigma. So what is this modular group? Well, it's SP2G of Z. So how should you think about that? Well, we have this surface sigma, and you could think of H1 of this surface. Okay, so H1 of some genus G surface has 2G elements, the different cycles of this surface. And there's a natural symplectic pairing on those cycles, which is where this SP comes from. And this modular group is just the sum over this symplectic group that acts on the space of cycles of your Riemann surface. Okay. If you don't want to work at genus G, you could also work at genus 1, where this is a sum over SL2Z, which is the modular group relevant for CFT on a torus. Okay. And this Eisenstein series, so if you look at a book on number theory and you look at Eisenstein series, you're going to end up learning a lot about holomorphic Eisenstein series. These are not quite those. These are what are known as real analytic Eisenstein series. They don't appear quite as often in physics, but they do appear in physics every once in a while. Good. And these are some, so this is just the answer that you get if you average this space of CFTs. And my goal in the last little bit of time I have left is to tell you why this answer that I have written down defines a theory of gravity. But before I do so, let me pause and see if there are any questions. So this is this slide and the last slide are the ones with lots of kind of ridiculous formulas. Now I'm going to shift to talking about the interpretation of these as a theory of gravity.
I have a quick question, Alex.
Please.
Is the measure unique in the averaging?
Great, good question. Okay, that's a great question, actually. So I defined a measure here that I didn't really talk about. So I noticed that the space of CFTs that I'm talking about is a coset space. So that means it's a homogeneous space, right? I mean, it's got OD, comma D isometry group. And there's a unique measure that is invariant under those symmetries. So there's a unique homogeneous measure on the space of CFTs with respect to the symmetries of your problem. So let me give you a simple example to make it a little bit more clear. So let's consider the case of a single free boson, D is equal to 1. Then this is a theory of a single scalar field, X, that lives on a circle of radius R. So in this case, the space of such theories is one-dimensional. It's parameterized by a single radius R. And we think of the radius of that free boson as a coordinate on the space of theories. And if you studied two-dimensional quantum field theory, you know that the signature property of such theories is T-duality. That is to say, the invariance under R goes to 1 over R. And so then if I were to ask you to write down a metric on the space of theories that is invariant under R goes to 1 over R, you would quickly find that the simplest metric you could write down is dr squared over R squared. Right? That's invariant under R goes to 1 over R. So we see that the symmetry of the problem has singled out a particular metric on the space of theories. And that metric is the one that I'm using. Okay. If you were to, I wrote down a single free boson using the more kind of physicsy compactification radius as the coordinate on the space of theories, but you could also think of R as a coordinate on O1, 1 mod O1, O1, 1 mod O1, 1 valued in Z, okay? And then this dr over R measure is the homogeneous measure with respect to those symmetries. It turns out that, oh, sorry, go ahead.
No, I just said thanks, Alex.
Yeah, it turns out that this measure coincides with what CFT people call the Zamolodchikov measure on the space of conformal field theories. We can talk about that more if anyone is interested. Yeah, go ahead. Is there another? Okay, yeah, good. So I think this is not the only measure on the space that you could talk about, but it's certainly the most natural one. And it's the one where I know how to compute this average. Although there are these things called the theta correspondence that I've come across that seem to allow us to compute these averages more generally, but I don't have anything useful to say about that. Okay. By the way, I should mention that I've tried to read the math literature where the Siegel-Weil formula is derived. It involves things like Adele's. Adele, I learned to my surprise, does not refer to a singer, but to something else. So actually, if you look at our paper, we actually gave a different derivation of the Siegel-Weil formula. I don't want to claim that this derivation is new, but I will claim that I couldn't find it anywhere. I mean, I sort of have a feeling that mathematicians know about this way of deriving the Siegel-Weil formula, but it's much more physics oriented. And it basically utilizes the symmetries of the theory. So this way of deriving the Siegel-Weil formula, we could talk about more if anyone is interested, really relies on understanding properties of this conformal field theory. And so it's kind of a physicsy derivation of this Siegel-Weil formula. Okay. But I don't want to spend too much time talking about the derivation of this formula. I'd really like to talk about its gravitational interpretation. So in particular, what I want to do is take the Siegel-Weil formula and interpret it as a sum over three manifolds. Okay. Now,
but would you mind just flipping back to the Siegel-Weil formula so we can look at it more?
Oh, the Siegel-Weil.
So there's a Laplace. Sorry. The next one.
Good. Oh, this derivation. Yeah. So the derivation. I mean, I can talk a little bit about how I think about this from a CFT point of view. Actually, maybe I'll mention that because the basic idea for those of you who studied conformal field theories is pretty cool. So the idea is the following: like we had a partition.
Sorry, before you explain that, I just want to understand what's written there.
Mm-hmm.
So that's the Laplacian.
Yes.
And it's with respect to Hg viewed as a metric?
Yeah. So this partition function is a function of two variables. It is a function of a even self-dual lattice, and it's a function of a period matrix. The even self-dual lattice we think of as an element of that moduli space, an arranged moduli space, which is a coset. And you can think of the period matrix as also being an element of a coset. So the period matrix is an element of Siegel upper half space, but Siegel upper half space is also a coset.
So the usual, I mean, genus one theta function satisfies a heat equation. Is this somehow or other higher dimensional?
Yeah, this is a version of that in general dimension. So
which is the time variable?
I mean, well, it's not. This is not actually a heat equation because this is a Laplacian, which is quadratic.
Maybe the first one. Sorry, maybe it's the first equation where you have space and time. Is that right?
I'm not quite sure what you mean. I mean, this is not a heat equation; it's a Laplace equation.
Yeah, the last one, but the previous one, you've got Laplacian on with respect to H, and another Laplacian on the moduli space.
Yeah. So the statement is that the two Laplacians combine, like each one of them does something horrific, okay? But when you combine them together, they do something simple.
Okay, so there's no first order derivation on the moduli space.
No, there's a different, if you ask me afterwards, I can talk, there's a different circumstance in which there's a first order equation, but that involves introducing additional data. Okay.
No.
But let me tell you where this comes from a physics point of view, because that's what I think is interesting. Because what are these two Laplacians? This is the Laplacian that moves you around in the space of Riemann surfaces. And this is a Laplacian that moves you around in the space of CFTs. Okay, so let's talk physics for a second. What is the operator that moves you around in the space of Riemann surfaces that your CFT lives on? It's the stress tensor. And what is the operator that moves you around in the space of conformal field theories? Well, that is the U1 current that generates this U1 symmetry. Okay. And the theories that we are looking at have a stress tensor that's given by what's known as the Siegel-Weil stress tensor. Okay. And so what that means is that moving around in the space of CFTs is the same as moving around in the space of surfaces that define your CFT. Okay. That's where this formula comes from. I mean, yeah, so good. Maybe, just in the interest of time, I can just take a, proceed. I realized I've already used up my hour. So let me just end by talking for a few minutes about this gravitational interpretation. So I want to interpret this Eisenstein series as a sum over geometries. And in particular, as a sum over three manifolds, whose boundary is my Riemann surface. Now I'm working in Euclidean signature, so these are going to turn out to be hyperbolic geometries. And in fact, if I handed you a surface sigma, and I said, find for me a hyperbolic geometry whose boundary is sigma, it's actually pretty easy to do. The simplest such geometry you're going to write down is a handle body. What is the handle body? A handle body is just the thing that you get when you take your surface, you embed it in R3, and you fill in the interior. Okay. So I've tried to indicate that on this slide here. So here you're thinking of your surface sigma. Here I've drawn a genus 2 surface, and I fill it in. So I've denoted here the filling in by indicating 2 cycles in purple that are contractible in the interior. Okay. And it turns out I told you my partition function was a function of the conformal structure of my Riemann surface. And it turns out there's a unique hyperbolic metric that for a given conformal structure on sigma. Now, it turns out that there are many different ways of filling in my Riemann surface sigma. Okay? And I want to interpret this Eisenstein series as a sum over the different ways of filling in my Riemann surface. In particular, remember, what was this Eisenstein series? It was a sum over SP2GZ. And what was SP2GZ? Well, that SP2GZ arose because on the space of cycles of my Riemann surface, there's a natural symplectic pairing. Okay? And in particular, how would I think about different ways of filling in this Riemann surface? So here I've drawn one way of filling in this Riemann surface by embedding it in R3 and filling in the inside. And when I did so, I chose a pair of cycles on my Riemann surface, right? These 2 cycles were the ones that were contractible. But it turns out that there are other ways of filling in this Riemann surface, and all they correspond to is different ways, different choices of cycles that can be made contractible. And how would you label different choices of cycles which are contractible? You would label them by the group SP2G that acts on the space of cycles. So what is the sum over SP2G? What is this sum appearing in the Eisenstein series? It is the sum over handle bodies that fill in my Riemann surface. And the sum in the Eisenstein series is just interpreted as different ways of labeling those geometries.
So Alex, going back to the ADCFT, is it that the original Riemann surface is the boundary and the handle body is the ADS?
Absolutely, absolutely. I mean, like it's useful to think about the genus 1 example, where a boundary is a torus, okay? And then this sum is a sum over SL2Z. And I can think about that sum over SL2Z as ways of filling in that torus with a solid donut. Okay. And in fact, in the physics language, we have different names for those ways of filling it in. You call one of them thermal ADS, and you call another one the Euclidean black hole. Okay. So there's a sense in which this sum over ways of filling in the boundary is related to black holes. In the torus case, this was sort of guesstimated 20 years ago almost, where it was known as the black hole fairy tale. What I've articulated, there were lots of problems with that proposal at the time. Among other things, the sums actually don't make sense. Here, this is a setting where all of the sums make sense. They're given by these Eisenstein series. More or less, you can do it at all genus. Good. I'm pretty well out of time, so let me just end with a couple of comments. So, okay, so I talked about the sum over geometries. There were also some loop corrections that appeared. It turns out this also works, you know, very in a very nice way that I won't go into in any more detail, except if people are interested. The only thing that I'll say is that the perturbative theory that we're studying is a theory of gravity that now seems to be simpler than Einstein gravity. In particular, it reflects the fact that I decided to study theories with such a huge symmetry group. So in particular, I considered theories that have this ginormous U1 to the D algebra of symmetries. This is going to lead to a bulk theory that has an enormous gauge symmetry. And in particular, it turns out to be something like a U1 Chern-Simons theory. One can compute in this U1 Chern-Simons theory and see that all of the bits and pieces fall together. And the result of this calculation is that we've interpreted this average over a space of conformal field theories as an integral over a space of lattices. It's a finite dimensional integral that we can compute, and it takes the form of a sum over geometries. And now I'm showing you the same formula that I showed you in the beginning of this talk, but you now understand more or less all of the terms in this formula. So on the left-hand side, we have an integral over a space of conformal field theories with some particular measure. So here, these lambdas are, this is an integral over a d squared dimensional space, finite dimensional integral. And on the right-hand side, we have a sum over geometries. And what are those geometries? They're handle bodies. Okay. Ways of filling in a Riemann surface. And what are the terms that are appearing here? They're the classical and one loop action of some theory of gravity that we could talk about in more detail if you like, defined that is going to be dual to this ensemble average over a space of CFTs. And finally, I'll mention that the lattices that we're considering, if you want to talk about a semi-classical theory of gravity, are going to be very high dimensional lattices. Okay. So the classical theory of gravity is some theory of high dimensional lattices, very closely related to problems of high dimensional sphere packing. But the classical theory that we're talking about here, it turns out, is not Einstein gravity. It's not Einstein gravity because I threw in all of these extra symmetries in order to solve the problem, right? Einstein gravity is presumably dual to an average over all conformal field theories, right? Not just conformal field theories with these extra symmetries. So because of that, you know, we threw in all these extra symmetries. It allows us to solve the problem, but we ended up with a theory of gravity that's not quite Einstein gravity. So for reasons that I didn't quite have time to go into, it appears that in this theory of gravity, you know, geometry and topology are a bit more ambiguous than we would expect in general relativity. Okay. Maybe in the interest of time, I'll stop here and just thank everyone for their attention. I'm happy to keep talking though, answer questions, address complaints, but maybe I'll just stop there. Thank you.
Okay, I think William's gone, so thank you very much, Alex.
Thank you.
Now, questions?
Good. I appreciate that some of the things that I presented were like way technical, so I'm happy to like try and unpack that a little bit for anyone who's interested.
Okay.
I have a qualitative question, Alex. So is there any way to generalize what you've done to a higher number of dimensions? And a lot was based on the complex plane as starting point.
Yeah. I mean, not easily, unfortunately. not easy. Like, unfortunately, the problem of, yeah, not easily. I mean, the problem is that, first of all, two-dimensional CFTs are very special. And I zoomed in on a space of conformal field theories that are basically integrable. Okay. Usually when we talk about 2D CFTs, we focus our attention on rational conformal field theories. Things like the CFT that governs the Eisen model or Potts model or something like that. In this case, the CFTs I'm considering are not rational in that sense, but they're still basically integrable theories. In higher dimensions, generically, like, I don't know of nice spaces of integrable CFTs that we could study along these lines. So yeah, it seems hard. It seems hard.
Other questions?
I have a couple of questions. I'm a bit puzzled by this gravity theory because, so if I just consider the Einstein-Hilbert reduction, right? Then in 3D, it's basically the same as SL2 Chern-Simons.
At the level of perturbation theory, yes.
At the level of perturbation theory.
I mean, presumably 3D gravity would also need to be augmented with some kind of sum over topologies that is invisible in Chern-Simons theory. I think that's an important point that people sometimes don't pay too much attention to, but yes.
Right, but I mean, also Chern-Simons theory is non-perturbatively defined. Mm-hmm. So if I just consider Chern-Simons theory as a full-fledged topological theory, then that's the statement is that that's not anymore Einstein-Hilbert gravity.
Precisely.
Non-perturbatively completed.
Precisely. So let me say it this way. Chern-Simons theory is defined, like, rigorously to define Chern-Simons theory, one would have to think about it as a sum over flat connections on a manifold of some fixed topology. Quantum gravity, all indications are, is not a sum over is not just a sum over metrics on a manifold of fixed topology, but also includes a sum over topology. Every attempt to define 3D gravity just as a Chern-Simons theory has failed and has needed to be augmented with some kind of sum over topologies. And that is my interpretation for what is going on here. So in particular, what we have here, so if I sort of had to zoom quickly through the last slide here, but the classical and one loop action that appear here are just the action of some Chern-Simons theory, and it's a U1 Chern-Simons theory.
Yeah.
But in order to get this theory of gravity, we had to augment it with a sum over topologies. And I think the same is going to be true for general relativity in 2+1 dimensions. Namely that it's going to be a Chern-Simons theory at the level of perturbation theory, in the sense that you could use Chern-Simons theory to compute all of the terms up here, but you would have to augment it by a sum over topologies. Now the difference is that general relativity, the relevant Chern-Simons theory is an SL2R Chern-Simons theory. The structure constants of SL2R are non-zero, unlike the case of U1. So that means that there's going to be an infinite perturbative expansion here. And that's one of the reasons why it's harder to study general relativity.
But then the boundary theory would be just a Wessumino Witten model.
Well, okay, we have to be careful. The boundary theory dual to Chern-Simons theory is the WZW model, but the boundary theory dual to gravity is not going to, full gravity, including the sum over topologies, is not a WCW model. We can see this even in the theory that I described today. Like, the WZW model that is dual to U1 Chern-Simons theory is, roughly speaking, the theory of U1 currents. Yeah. So in particular, it would give you this one loop determinant, but it wouldn't give you this theta function. Right? Look at this example here. What is what is this guy here? That's literally the character that counts U1 descendants. Okay. It's the otherwise known as the U1 conformal block on the torus. Okay. Yeah. And so, and this one loop determinant here is just another kind of conformal block. That's some kind of higher genus conformal block. The point is the thing that is dual to Chern-Simons theory is kind of the perturbative piece of the boundary theory. But all of the interesting stuff that happened when we averaged came from this theta function. And that's not visible in the Chern-Simons theory in the bulk. It's the thing that turned into the sum over geometries. Mm-hmm. So it's not like, it's not like, people often, like, 3D gravity is not equal to, like, Chern-Simons theory is a useful tool for doing computations in 3D gravity because it lets you compute at all orders in perturbation theory, at least in principle, but it's not the same. I mean, let me say that, in the case of 3D gravity, general relativity, people have tried to make this more precise. So for example, if you just study SL2R Chern-Simons theory, and then you look at the WCW model, you actually end up getting something that looks a lot like a Liouville theory on the boundary. Mm-hmm. And the Liouville theory, it doesn't have a normalizable ground state. It has a continuous spectrum. It doesn't obey Cardy's formula. It has all kinds of features that would make it sort of unacceptable as a theory of gravity. Okay, it's not a compact unitary CFT. Like, Cardy's formula is the Blackwell entropy. Like, let's put it this way. My definition of an interesting theory of gravity is one where you can understand Blackwell entropy. Blackwell entropy is Cardy's formula. Liouville theory doesn't obey Cardy's formula. So. Mm-hmm.
I see.
Good, great questions, though. Yeah.
Well, thank you. But I actually have another question, which is here you are always considering compact boundary surfaces, right?
Uh-huh.
But I could consider some puncture surfaces. Well, in terms of the Chern-Simons, if you want, I could think of them as some singular boundary conditions for the connection. But presumably, one should be able to do it anyway, also here by using just some vertex operator insertions.
Yeah, you would need to decide what operators you're inserting punctures. Yeah, I don't see why you couldn't think of that.
And so has any of this been considered, and what would that mean in the gravity in this case, having some punctured?
I mean, let's start with the simplest case. So you could start with a sphere with 3 punctures, otherwise, basically a pair of pants, okay? Mm-hmm. And then you would need to insert some operators at those punctures. Let's call them O1, O2, O3. And then the CFT partition function with those 3 punctures has a name. It's the operator product expansion coefficient, C1, 2, 3, okay? And so then if you were to do a gravitational calculation of such an object, you would be computing some kind of universal gravitational contribution to this OPE coefficient. Mm-hmm. And there are things we could say about this. In the theory that I was describing in this talk, where it's based on free bosons, this is probably kind of trivial because it's a free theory, so all the OPE coefficients are basically 0, or I should say they're basically just delta functions determined by conservation of U1 currents. So I don't think there's anything super interesting to say about this in the U1 theory, although I could be wrong. But in more interesting gravitational theories, I think this is something worth thinking about. There's many things one can say. So for example, you can try and give gravitational formulas for these OBE coefficients, and you would interpret those gravitational formulas as averages over a space of CFTs, right? So you could try, I've actually written a bunch of papers where I give gravitational, I've written formulas where one can derive things like this, but not in this precise sense, not in an average over CFTs, more as an average in a given CFT. So I would really like to think more about that, but I don't have anything really interesting to say right now.
Okay, thank you.
Great, thanks.
Thank you.
Thanks for the questions.
I think that, I don't know if there are more questions, but I guess we should call an end to the seminar because we're 15, 20 minutes over. So thank you again for your talk.
Thank you.